Hi. Welcome to the animation talk on Friday afternoon. We are opposite a Kotlin talk, so I think that means that everybody in this room didn't want to hear about Kotlin, which is perfect because we don't have any Kotlin on our slides. So welcome to the not Kotlin talk. I am Chet Haas. I'm from the Android UI Toolkit team.
I'm Doris Liu. I'm also on Android UI Toolkit team.
And we're going to tell you a little bit, actually a lot about animation. We're going to talk about small changes that were made to the existing Animator stuff, small but very important and deceptively tricky to implement features. But more importantly, Doris is going to tell you all about a new physics-based animation system starting right about now.
Clicker. All right. So today I'm going to talk about physics-based animation. You might be asking, why would we need a physics-based animation library? A few years ago, before I joined the Android framework team, I was an app developer, just like some of you. I wanted to create a swipe animation for the Google camera app. And I had the camera menu moving in a beautiful waveform along with the gesture. I also tracked the velocity of the gesture up until the moment of finger release. Then I thought to myself, all right, now the only thing that's missing in this is getting the camera menu to continue the momentum of the gesture once the finger is released. So I looked into the Android animation framework for an API that can take velocity as one of the starting conditions and close the gap for me. I looked and looked, and there was no such API. If you've had similar experience building animations in your app, you're in luck. Because today we're going to talk about the new physics-based animation library that we have just released. You might be asking, how is this new physics-based animation library any different than the existing animation API? Well, if you're familiar with the existing animation API, you know in order to create an animation, you will need to provide a start value, an end value, a duration, and an interpolator. Velocity? That's just an afterthought. Once such an animation is created, velocity has to be derived from other properties of the animation. Given that, it's extremely difficult to create an animation that can continue the momentum of the gesture once that's leading up to the animation. But with physics-based animation, it can handle the different gestures with different velocities much easier, and different gestures from small swipe to a really fast fling. Also, because the movements of the animation in the new system are governed by real-world physics, they look more natural and lifelike. And the new system can also respond to updated user input and dynamically change the target value of the animation during the animation. Now let's take a look at how different animation systems handle this target value change during the animation. Here we're using an object animator. I think some of you might be familiar with this. And the target value is indicated by the position of the green ring on the bottom. As you can see, the ring had moved before the animation is finished. And usually the way we handle this is we would cancel the ongoing animation and then reconfigure the animation using the new end value, and then starting it again. But the problem with that is, as you can see, it leads to a really sudden and abrupt change in the movement. And if we look at the velocity chart for this animation, the blue and red curves in here represent the velocity x and y. At the moment of target value change, the velocities are dropped immediately back down to 0. And that's because we have canceled the ongoing animation. And then the velocities will start changing again once the new animation starts. But this discontinuity in velocity can create a really jarring experience for the user. In contrast, here's physics-based animation. When the target value is changed in physics-based animation, we interpret that as a change in the physics force. And then the new force will continue to act upon the existing velocity of the object, which is why we won't see a velocity discontinuity. And in this example, we can see the transition to the new target position is really smooth. And similarly, let's look at the velocity chart. And we're no longer seeing any discontinuity in the velocity, and that is the key to a smooth animation. At this point, you might be asking, so what exactly is this physics-based animation? The way we define it is, it's an animation that's driven by force. And based on the force, we can calculate the acceleration or deceleration, which we can then use to calculate and update the velocities and values for the animation. Until finally, when the force reaches equilibrium, that's our signal to stop the animation. First, let's take a look at fling animation. Fling animation starts with the initial velocity, and usually that's the velocity of your gesture. And then it will continue that momentum, and then gradually comes to a stop. The force behind fling animation is a friction force, which is proportional to the velocity. What that means is velocity will undergo an exponential decay in the duration of the animation, and that will produce a very graceful end to the animation. And by the way, this fling animation is exactly the API that I was looking for years ago when I was building that animation for the camera app. Now let's see an example for the fling animation. Here, as you can see, I'm flinging this list from left to right. And the orange dot is indicating the position of my finger. And the list just took off at the same velocity of my gesture, and then gradually come to a rest. Now let's see how this is achieved. In order to get notified when a fling gesture occurs, we need to create a gesture listener. And once the fling gesture is detected, we'll receive this on-fling callback with a down event, an up event, and the velocity in both x and y axis. And we'll be using, and they'll be in the unit pixels per second, which is also the unit that we'll be using for the velocities in the new animation system. And now we're ready to create a fling animation. To the constructor of the fling animation, we need to provide the object we want to animate. In this case, it's the list of bearded androids. And the property that we want to animate, in this case, that is the square x, since we want to fling this list horizontally. And then we're going to set the start velocity. Here you can see I have inversed the velocity of the gesture. And that's because here we're animating the square property. The square property is sort of special in that a positive change in the square value would actually move the list in the opposite direction as a positive velocity would. And then we're also going to set min value and max value to define the range for this animation. Fling animation would end immediately once it reaches either its min value or max value. And I would encourage you to set a good value range for your animation so that as soon as the animation goes off screen, it should stop right away. Otherwise, the animation might go on for too long without making any change on screen, while it would request for redraws and consume a lot of battery. And finally, we're setting friction to control the rate of deceleration. Now we're ready to start. So this is all it takes to create a fling animation. Now let's take a closer look at the fling friction. Here I'm going to create an animation for the view's scroll y property with a starting velocity of 5,000 pixels per second and a friction of 1.1. And then I'm going to create another animation with the exact same setup, except we're going to double the friction. And if we run these two animations side by side, we can see how the friction affects the look of the animation. As you can see here, with a smaller value of friction, the animation would go on for much longer, whereas when the friction is higher, naturally it decelerates the movement a lot faster, causing the animation to stop a lot sooner. And you can configure the friction to whatever positive value that looks good for your animation. In addition to fling animation, we've also introduced spring animation in our new animation system. Now, first, let's create a spring animation. Here, to the constructor of the spring animation, we're going to supply the object we want to animate. In this case, it's a view. But it doesn't have to be a view. It can be any object. And then the property we want to animate, in this case, is a translation y of the view. And then finally, the resting position of the spring. Now we're ready to start. So this animation would animate the view from whatever translation that it had at the start of the animation to back to 0. And here's what it looks like. As you can see, as I'm pulling this little Android down, it's moving its translation y while stretching the spring as it goes. And then once I let go, that's when the spring animation would start. And then the translation y would start from where I released it back to 0. And you can see it bounces back up and oscillates a little bit before it rests at translation y of 0. And if you feel adventurous, you can also change the bounciness of the spring by simply setting the damping ratio. Here, we're going to set the damping ratio to not bouncy at all. And that's what we see in the animation. If you look at this animation and you feel like this doesn't really match your taste for spring animations, we have an easy fix. You can simply change the damping ratio to high bouncy, and then you will have a very bouncy animation with a lot of oscillation before it finally settles. In addition to damping ratio, you can also change the stiffness for the spring, which will control how quickly the object would return to its resting position. And we'll take a look at that in a moment. Now, before we start the animation, we can also set some starting conditions for the animation. For example, if we set the start value to 200, this animation will go from a translation y of 200 back to 0. And also, we can set the start velocity to match the existing movement of the object, creating a continuous motion. We can also set the min value and max value, like we did for fling animation, and define the range for the animation. Now we're ready to start. So let's take a look at the stiffness from low to high. Here, if you look on the very left, when the stiffness is very low, the spring compresses rather slowly after it's stretched out of its resting position. And when the stiffness gets higher towards the right, it bounces back up much faster. And these are the 4 spring stiffness constants that we have already defined in our system, because they each provide a somewhat unique look. You can use one of these already defined constants, or you can use any positive float value for the spring stiffness in your animation. Now that we've seen how we can animate translation using spring animation, let's see what we can do when we combine the rotation and translation together in the spring animations. Here we have an example of that. As you can see, as this list flies in, each individual head sort of shakes around as if they were hanging on to a clothesline that we're pulling in. To achieve this, we need to apply a rotational spring force on each individual head, along with the translation animation to slide this whole list in. First, we need to rotate each individual head. We need to go through all the items on the list. And for each item, we'll need to create a spring animation on its rotation property. And you may have noticed here I'm using a different spring animation constructor as we did before. And this constructor doesn't require a third parameter, which is the resting position of the spring. When using this constructor, the spring animation won't create a built-in spring force. And it would instead expect a custom spring force to be passed in. And that's what we're going to do. We're going to create a custom spring force of a resting position of 0 and a damping ratio and stiffness that looks good for this particular animation, arrived at through careful experimentation. And you might ask, why do we want to use a custom spring force instead of the built-in spring force? And the answer is, by creating a custom spring force, we can then share this spring force across all the spring animations for the children. Note, this is only viable when all the spring animations here expects the same spring constants and the same resting position. And finally, we can set the start value of the rotation animation to -25, so that each head would rotate from a -25-degree angle and then oscillate around 0 degree and eventually come to a stop. Now that we've rotated each individual head, we still need to slide this whole list in. We can do that by creating a spring animation for the list on its translation X property. And similar to the rotation animation, we're going to configure the spring constants. Here, we're going to use the same spring constants as we did before. And finally, we're going to set the start value so that the translation Y would start from 400 and then slide back into place. So we've seen spring animations on rotation and on views translation. What if you want to animate something that's not a view property? Well, good news is physics animation supports that. Here's an example of that. As you can see, when I tap on the little mustache icon, all the items just pop in and blow up beyond its normal size and then shrink back down, making a very dramatic entrance. And we could achieve this by creating not one, but two spring animations for each individual child. One on its scale X property, the other one on its scale Y property. So each individual head would be able to scale along both the X and Y axis uniformly. But that's a lot of work. Now let me show you a different way to do this. Imagine, what if view group had this property, let's call it child scale. And whenever child scale changes, the view group would propagate down that change to all its children in both the scale X property and scale Y property. And in that case, we can just animate this one child scale for the view group, and then we're done. Even though view group doesn't really have this property, we can create one for it. Here, we're going to create a custom property using float property compat. And we're going to have to override the set value and get value. Whenever the child scale changes, we will receive this set value callback. And in that, like we mentioned, we're going to pass down the change to all the children and then change their scale X and scale Y property uniformly. And in the get value, since we're assuming all the children to have the same scale, we can just return the scale of any child. In this case, we'll just return the first child. Now that we've created this custom property, we can put it in an animation. So we're going to create an animation on the child scale property for the list of beers. And again, we're going to set the stiffness. If you remember, stiffness changes how quickly the object returns to its resting position. Here, because we want the scale change to be more graceful, we want to use a low stiffness. And finally, we're going to set the minimum visible change. And this is a method that we haven't seen before. What it does is it provides the animation system a hint as to when it would be a good time to stop, so that the animation doesn't go on for too long without making any visible change on screen. And the reason why we haven't seen this method before in all these previous examples is because up until this example, we had animated only the built-in view properties. And when we animate built-in view properties, the animation system can derive such a value based on which property is being animated. Here, since if you create a custom property, you will need to provide the smallest change in your custom property that can make a visible difference on screen. In our case, we're animating child scale, which is essentially a scale property. So we're going to use the already defined constant mean visible change scale. And then we can set the start value. to 0.5 so that the scale animation starts from a half scale and then blow up. And then eventually, it will settle at scale of 1, its normal size. So we've talked about fling animation. We've also seen some cool effects from the spring animations. Let's see what we can create by combining these two. Here, we're going to use the same example as we did, or same list as we did for the fling animation. As you can see, I'm flinging this list back and forth. But as the fling animation gets to the end of the list, there's still some velocity left. There's still some remaining energy. And that's when the list starts to stretch out and snap back like a rubber band. This is a very playful way to dissipate the remaining energy when arriving at the end of the list. And I think you will agree with me, this is a much better experience than harshly stopping the motion and losing all the momentum. In order to achieve this, we first need a fling animation. And we're going to just use the same fling animation as we did before. Except this time, I'm going to call out the set min value and set max value. These define the range of the animation, like we mentioned before. But this range ensures that the fling animation would end immediately upon reaching either end of the list. And that's when we can start the spring animation to then take over whatever momentum that it has left. So in order to start a spring animation right after the fling animation, here we're going to use an on-animation update listener. Once the fling animation finishes, we'll receive this on-animation end callback with a fling animation and whether or not it's canceled, and then the scrolling value and the scrolling velocity. If the velocity is high enough, then we're going to create the spring animation for the stretching effect. And we're going to create the spring animation for this whole list on its scale x property so it can stretch horizontally. And as always, we're changing the spring constants to make the animation look good for this particular case. And finally, we're going to set the start velocity. Here, you might notice I'm not using the velocity that I received from this callback, because that's the scrolling velocity, which is pixel-based. And for our scale animation, we want something that's in terms of scale. We can do that conversion by simply dividing the velocity by the size of the menu. Now, before we start, we still need to configure one last thing, which is the pivot point. And that's for the scaling. As you can see, I'm really flinging this list back and forth. And depending on which way I'm flinging it, I want the stretching to go the same way as the scrolling direction. So when the velocity is negative, the list is scrolling to the right. And I want the stretching to go towards the right as well. That requires us to pin the list on its left side. And we can do so by set the pivot x to 0. Similarly, when the list is scrolling to the left, we want to pin the list on its right side. And we can do so by set the pivot point to the right side of the list, which is the width of this list. Well, we've seen each individual animation, each individual spring animations in the past slides. And I think we can create something that's more advanced and more complex if we build on top of that, such as chain springs. Here we have 3 views that are chained together via spring force. And you can see I'm dragging the top view around, and the white circle indicates the drag point. And the other 2 views would follow as the top view is moving around as if the 3 of them were attached to each other by a bungee cord. Now let's take a look at how we can achieve this. Let's name these 3 views lead, A, and B for easier reference. So our goal is to have A follow the lead as lead is being dragged around, and B follow A. And we're going to achieve this by using spring animations. Let's first take a look at how we can have A follow the lead. So first, we're going to create animations for A on its translation X and translation Y properties. And in the on-touch listener, where we're going to process the touch events and move the lead view around, we're going to first, for each move event, we're going to compare this event against the last event in terms of position. And then we calculate the delta, and this delta would be the amount of movement of the finger. And then we're going to apply the delta to the lead view's position so that the lead view would be moving the same amount as the finger. Once the lead view's position is updated, we want to update the position of, or the animation for A, so it appears like A is following the lead. And here we're going to use a method called animate to final position. And we haven't seen this method before. It acts one of two ways. If the animation is not yet started, this method would set the final position for the animation and start the animation. If the animation is already started, is already running, then this method would just update the final position for the animation. And what this means is every time we receive a move event, we're going to move the lead view. And then if A is at resting position, we're going to start animation to move A towards the lead view. If the A is already animating, then we're going to update A's final position so that if you remember in one of the earlier slides, the way physics-based animation handled target value change, A would eventually, after some course correction, it would eventually head towards the lead view. And this is how we achieve having A follow the lead. And finally, we're going to update the last position for the motion event for the delta calculation. Now let's take a look at how we can have B follow A. Similarly, we're going to create animations for B. And in order to get notified whenever A's position is changed, we need this on-animation update listener, and we're going to add the listener to A's animation. And in the on-animation update callback, we're going to receive A's animation, and then A's position, and A's velocity. We're going to do the same trick here. We're going to call animate to final position. So if B is not moving at the moment, then we would set the final position for it and then start the animation to move it towards A. Or if B is already moving, we're going to update its final position, so eventually head towards A. So the physics-based animation is available now in SupportLib 26 beta 1. And you can use it by adding this dependency to your Gradle file. And it's backward compatible to API 16. And I'm very excited to see what you guys can come up with using this library.
Awesome. So that was the cool new stuff, but what if you're still using the cool old stuff? So that's what I'm here for. So AnimatorSet, there was long requested functionality in terms of being able to seek within an animation as well as reverse. We have this in the Value Animator API, but not in AnimatorSet because it was difficult to do. So now we have these capabilities, and I'll show a simple demo and some code that's not written in Kotlin, and you can see how to do that. So there's a famous quote that I think everybody probably knows, seek and you shall find. It turns out that this was taken out of context. The full quote goes something like this. Seek and you shall find that there is no seek API on AnimatorSet. Right? Nobody knew that, but I'm here to tell you that. Also, it turns out that there's no way to reverse it. But we did some things about that, and I'm going to show you how you can use that functionality. So here we have a really simple, rather lame demo what I want to do, given this amazingly complex UI, is move those 3 buttons around on the screen when the user clicks on the various controls there. So in particular, when you play the animation, I want the button on top to move to the right, the button in the middle should move down to the right, and the button on the bottom should move straight down. So the button, when it moves to the right, you create an object animator, fairly straightforward. We're going to animate translation X, and we're going to move it all the way over until it's positioned all the way over on the right. The button in the middle, we're going to move it to the lower right. Similarly, we create an object animator. We can use property values holder so that we can animate X and Y at the same time inside the same single object animator. So we're doing translation X and translation Y in parallel. And finally, the button on the bottom is going to move all the way to the bottom of the screen. Similarly to the one at the top, it's going to animate translation Y all the way down to the bottom. So we create these things, and then we create the animator set that contains these child animations. We're going to run them in sequence, so it's going to go top, middle, bottom. So we'll play those sequentially, and then we start the animation, which looks something like this. I bet you couldn't guess what was going to happen there. So you press the play button, animation plays, fairly straightforward. That's what you could do already. But what happens if we actually want to seek within the animation? Well, now we call this new method called setCurrentPlayTime. So we've hooked this up to the seek bar at the top. So when we get a callback into the onProgressChanged method, we can see where the seek bar is in that track that it's in, and interpret that as a percentage of movement, and then apply that to the AnimatorSet animation. So set current playtime using that percentage multiplied times the total duration that the animation has. So we have this get total duration method on AnimatorSet. We get that, multiply it times the percentage, and away we go. So we drag it around on the screen. Buttons move. All the child animations are moving independently depending on where we've seeked in the AnimatorSet animation itself. All right, and then finally, I bet you couldn't guess how this is going to work. What if we want to reverse the animation? So the user clicks on the reverse button, and everything moves in reverse. Very straightforward. It turns out that the entire quote is now amended, and it's now until now. So please use reverse and seek. And get the capabilities that you want. A couple of notes on that. One is that it will specifically seek within child animations that are a value animator, because if it's not a value animator or an animator set, we're not sure how to reverse or seek that thing. Right? So if your child animation is just an animator, it's this opaque thing that you've implemented, we're not sure what to do about it. That will get dropped on the floor, or you can implement that functionality. But it's really specifically for the common case of value animators and object animators, subclass of that. Another thing to note is there is new on-animation start and on-animation end callbacks in the interface, default methods that we implemented that will then provide you the direction. So in addition to knowing when you're starting and ending, it's useful if you know what direction you're running in, given the new capabilities that AnimatorSet has, so you can access those as well. And that is the talk. And we do have, sure.